Okay, Bismillahirrahmanirrahim. So in this video we are going to go through example 8.3. The question is the figure 8.17a shows a 100 horsepower 250 volt 1200 rpm shunt DC motor with an armature resistance of 0.03 ohms and a field resistance of 41.67 ohms. The motor has compensating windings, so armature reaction can be ignored. This is good for us, makes the problem more simple to solve. Mechanical and core losses may be assumed to be negligible for the purposes of this problem. The motor is assumed to be driving a load with a line current of 126 amps and an initial speed of 1103 rpm. To simplify the problem, assume that the amount of armature current drawn by the motor remain constant. And the question is, if the machine's magnetization curve is as shown in figure 8.9, what is the motor speed if the field resistance is raised to 50 ohms? Okay, and the schematic diagram at the bottom shows us the equivalent circuit of the shunt DC motor. And here is the magnetization curve, and please note that this is for the speed of 1200 rpm, which is the base speed of the motor. Okay, so there are a few values here that we are going to use in our calculation to answer the question, which is this is the armature resistance RA, yeah, and then here we've got field resistance, which is RF. However, we've got two of them, yeah? The first condition and then the second one, so we call them RF1 and RF2 respectively, right? And then we've got here the line current, which is IL, which is shown here in this diagram, and then we've got the initial speed, yeah, call it N1 equals to 1103 just rpm. Okay, okay, now let's try to answer the question step by step. So as the example mentions that there are two conditions. First is when the when the RF is equal to 41.67, yeah? And second is when the RF is equals to 50 ohms. This value here is actually the sum of RF and R adjustable. If you see on the schematic diagram, is this RF plus R adjustable. Yeah? Okay, when in the first condition, RF is equals to 41.67 ohms, here let's call it RF1. In this condition, we will have the internal generated voltage EA1 is equals to constants times flux 1 and 1. Yeah. Okay, later in the second condition, EA2 will be equals to K flux 2 N2. Yeah. This will be when RF is equals to 50 ohms. Okay, so first and second. Right, next what we been told in the example is that we should assume that the amount of armature current remains constant. So what we have here, the armature current is IA is constant, which means that IA1 is equals to IA2. Yeah. Okay, now if you look at the equivalent circuit, this is IA. Okay, I have just circled it in red. It's a bit too thick. Okay, so this is IA, and then we've got RA here, the armature resistance, and then we've got the internal generated voltage here, while this voltage, yeah, across here, this voltage is the same as VT if you look at, which is because this nodes actually connected to the terminal nodes, these two nodes on the right hand side here. Okay, so from there we can write down that by using KVL, VT is equals to EA plus IA RA. Okay, and therefore if we rearrange this, EA is equals to VT minus IA RA. Okay, now if we look at this equation, VT is constant, which is 250 volt, and IA is also constant. Yeah, IA is constant. We've been, as we can see from here, this is the assumption that we should use based on the example statement. And then we've got RA, which is also constant. So what it means? It means that EA is also constant. Yeah, and therefore EA is constant, and therefore EA1 is equals to EA2. Yeah. Now if we write down EA2 divided by EA1 to find the EA2 is equals to this. Yeah. Can you see on the top? K pi 2 and 2 divided by EA1 is K, the constant, K prime, pi 1 and 1. Yeah. Okay, and we can cross the K out because these two are the same, and EA2 is equals to EA1, so this is equals to 1. Yeah, this is equals to 1, and therefore what we have in here is that pi 2 times n2 equals to pi, over pi 1 and 1 is equals to 1. And therefore, because we want to find the second speed, which is n2 is actually equals to pi 2 over pi 1 into n1. Okay, and n1 is known already, so if we can find the ratio of these fluxes, yeah, then we should be able to work out the value of the new speed n2. Okay, so now our task is to find the ratio of pi 2 over pi 1. We are going to use the magnetization curve. Yeah. And remember, for magnetization curve, it applies for only one speed, yeah, which is 1200 RPM. Okay, and the base rate okay, and we've got two conditions here when we've got RF1 and when we have RF2, and therefore the EA0, yeah, the internal generated voltage at the base speed, will have two different values. So let's call them EA01 and EA02. And the equation for this is just like what we have before. And pi, these are 2. Okay, but because we know that the speed is the same, so n1 is the same as n2, and therefore if you write them down in ratio format, because n1 is the same as n2, then we can cross this 2 out. And then how about the EA01 and EA02? EA01 and EA02, actually we can find the value if we know what is the field current for each condition. Yeah. Okay, let's have a look again at the magnetization curve. Here, if we know the value of the field current, by using the graph we can find the value if we know the field current, the value of the field current, then we can work out the terminal voltage VT. Yeah. Then let's work out first what are the field current for each condition, the beginning and the second one. Okay, when RF one equals to 40, what is the value again? 41.67. And RF2 50 ohms. Okay, so here the field current, if you look at the schematic diagram or the equivalent circuit, is simply equals to Vt over Rf, which is 250 divided by 41.67. Okay, which is, so If1 is equals to 6.0 amps. Okay, and then if you follow the same step, you'll find that If2 is equals to 5.0 amps. Okay, so you've got 6.0 and 5.0. Now we use the what we call the magnetization curve. So If1 is 5.0, which is here. Okay. Then you can use the rho. Okay, I don't want it to be accurate, but it's not. Okay, that's it. So it's something like here, this here, just the 5 amps, and then you'll find that the Vt is equals to Vt is equals to 250 volt. Okay, and then if you follow the same step for the 6 amps, this is what you should get roughly. It's not easy to read from the scale what is the actual value, but if you are cheating a bit from the book, it says it's 268 volt, yeah? While for this 5 amp it was 250. So by using the curve, then we know for the If1 we've got the EA01, which is the internal generated voltage at the base speed 1, which is referring to when the RF equals to 41.67, EA0 is equal to 250 volt. Yeah? And this one EA02 is equal to 268 volt. Okay, therefore then if we fit this information into this equation, we've got that 250 over 268 is equals to remember that we can cross this 2 out as well, is equals to pi 1 over pi 2, and therefore now we have the value for this ratio, and then if we rearrange this a bit, pi over pi 1 is equals to 268 over 250, which is 0.076, and now we can simply fit this into this equation here, and therefore now we can find that N2 is equals to 1.076 times N1, and N1 is if you refer back to the question, it says this is the value of N1, 1103. So 1.076 times 1103, and this should give us 1087 RPM. Yeah, so that's the answer.